A rocky planet circles the nearest star to the Sun, just over 4 light-years away. Known as Proxima b, it was discovered in 2016 through precise measurements of the tiny gravitational wobble it induces in its host star, and has since been confirmed by years of additional observations. It may lie within the star's habitable zone, where temperatures could allow liquid water to exist under the right conditions. In astronomical terms, it is our closest potentially Earth-like neighbour. Yet that proximity is deceptive. 4 light-years sounds small until it is translated into distance, tens of trillions of kilometres of nearly empty space. At the speeds achieved by today's spacecraft, the journey would take tens of thousands of years. Even the most ambitious propulsion concepts currently proposed remain theoretical and would still require decades to complete the crossing. The challenge of reaching Proxima b is not simply a problem of building a better rocket. It is a confrontation with the fundamental realities of energy, distance, time, and the laws of physics themselves. The number that does not mean what you think it means. Proxima b is 4.24 light-years away. That statement appears in every article about the planet, in every documentary segment, in every educational context where the planet is introduced. It is the number that makes Proxima b sound reachable, 4.24. It is a small number. It is smaller than the number of floors in many buildings. It is smaller than the number of years most people spend in secondary school. The phrase 4 light-years away has a quality of approachability that is entirely misleading, and the misleading quality is not accidental. It is a consequence of using a unit that compresses the actual distance into a form the human brain can handle while stripping away most of the information that matters. A light-year is not a year, it is a distance. It is the distance light travels in 1 year, moving continuously at 299,792 kilometers per second in a vacuum, the fastest speed that any physical thing can move. In 1 second, light crosses the distance from Earth to the Moon 7.5 times. In 8 minutes and 20 seconds, it covers the 150 million kilometers from the Sun to Earth. In 4.24 years, it covers the distance to Proxima Centauri, the nearest star. That distance is approximately 40.2 trillion kilometers, written out in full. 40,200 billion kilometers. 13 digits before the decimal point. No unit of everyday human experience maps onto this number in any way that preserves its meaning. The distance from New York to Los Angeles is approximately 4,500 kilometers. The distance to Proxima b is roughly 8.9 billion times that. If you scaled the solar system down so that the Sun and Earth were 1 meter apart, Proxima Centauri would be at a distance of approximately 270 kilometers. If you drove to it at highway speed, the drive would take about 3 hours. But the solar system at that scale would be a 1 meter gap in a 270 kilometer journey. The solar system that took humanity all of its history to begin exploring would be invisible, a gap smaller than a thumb in the distance to the nearest star. This scale problem is not merely a matter of numbers being large. It has specific, concrete consequences for every aspect of the challenge of reaching Proxima b. The amount of fuel needed to cross this distance is set by this scale. The duration of any mission is set by this scale. The communication delay between a spacecraft and Earth is set by this scale. The degradation any physical system experiences over the crossing time is set by this scale. The probability that any particular component fails before arrival is set by this scale. Every problem in interstellar travel is, at root, a problem of the number 40,200 billion kilometers. And the reason that number is so problematic is that it is not merely large, but large in a specific way. It is many orders of magnitude larger than anything that has ever been successfully crossed by a human-made object carrying scientific instruments and returning useful data. Voyager 1, launched in 1977, is currently about 23.5 billion kilometers from Earth, the most distant human-made object ever built. This is genuinely extraordinary. No object manufactured by human hands has ever been so far from its origin. And yet Voyager 1 has covered approximately 0.06% of the distance to Proxima Centauri. If the journey to Proxima b were a marathon of 42 kilometers, Voyager 1 has run roughly 25 meters in 47 years of continuous travel. At the speed of 17 kilometers per second, which is itself faster than any human-made object before it reached this velocity, Voyager 1 would need approximately 74,000 more years to reach the distance of Proxima b if pointed in that direction, which it is not. 74,000 years. Human writing has existed for approximately 5,000 years. Agriculture began approximately 12,000 years ago. The number 74,000 does not describe a journey that requires better technology. It describes a journey that requires a fundamentally different framework for what technology means. The number 4.24 light-years sounds small because the light-year is a large unit chosen for human convenience, not for physical intuition. If astronomers had instead measured Proxima b's distance in kilometers, every article would say the planet is 40.2 trillion kilometers away, and the intuition that this is reachable would not survive contact with that number. The compression of scale built into the light-year unit is useful for discussing distances between thousands of stars. It is actively misleading when applied to the question of whether a specific destination is practically accessible to human beings within any time frame that the word practical can be attached to. What light years actually measure against what we have built. Understanding the gap between the distance to Proxima b and the farthest any human technology has travelled requires moving beyond the abstract comparison and looking at the specific, documented performance of the fastest objects humanity has ever created. These objects represent the current actual ceiling of human propulsion capability applied to space travel. They are not hypothetical. Their velocities have been independently verified, their missions documented in detail, their trajectories calculated and confirmed. Against these real numbers, the distance to Proxima b can be assessed not as a philosophical challenge, but as an engineering constraint with specific consequences. The Parker Solar Probe, launched in 2018, achieved a heliocentric velocity of approximately 163 kilometers per second during its close perihelion pass near the Sun in late 2024, the fastest speed ever recorded for a human-made object. This speed is roughly 0.054% of the speed of light. At 163 kilometers per second, the Parker Solar Probe is moving faster than any human-made object has ever moved in the history of spaceflight. It is faster than any rocket exhaust, faster than any projectile weapon, faster than almost any physical process in everyday experience. It achieves this speed by falling toward the Sun and gaining kinetic energy from the gravitational field, then using a Venus flyby gravity assist to reshape its orbit for the next perihelion. The velocity is real, confirmed and astonishing by human standards. At 163 kilometers per second, the Parker Solar Probe would take approximately 7,800 years to reach Proxima b. That is more than twice the documented history of organized civilization on Earth. The fastest object humanity has ever created would need to operate continuously for longer than the span from the construction of the earliest known cities to the present, and longer still to cross the distance to the nearest star. This is the actual state of human propulsion capability as of 2025 applied to the nearest interstellar target. The New Horizons spacecraft, which flew past Pluto in 2015 after a 9.5-year journey, travels at approximately 14 kilometers per second relative to the Sun. It would require approximately 90,000 years to reach Proxima b's distance. The Voyager probes, at approximately 17 kilometers per second, would need the 74,000 years calculated in the previous chapter. These are not slower vehicles that a faster rocket could improve. They represent the category of chemically or gravitationally accelerated spacecraft that has been the basis of all space missions to date. Within this category, the Parker Solar Probe's 163 kilometers per second is close to the practical ceiling because it requires the gravitational focusing of a close solar pass to achieve, an approach that cannot be used to direct a spacecraft toward another star system, because the solar system is not positioned to provide a gravitational slingshot aimed at Proxima Centauri with the required energy. The specific question of what velocity would be needed to make a mission to Proxima b feasible within something resembling a human timescale can be answered precisely. At 10% of the speed of light, approximately 30,000 kilometers per second, the crossing time to Proxima b would be approximately 42 years, not including acceleration and deceleration phases. A spacecraft launched in 2025 at 10% of light speed could arrive at Proxima b in the 2060s. The crew members who departed as young adults might arrive as old people or might not survive the journey, but the duration is at least in the range of a human lifetime. At 5% of the speed of light, the crossing takes roughly 85 years, approaching the biological limit for any current human. At 1% of the speed of light, 3,000 kilometers per second, the journey takes approximately 424 years, requiring multi-generational planning. At the Parker Solar Probe's record-setting 163 kilometers per second, the journey takes 7,800 years, which is outside any institutional, cultural, or biological framework that human civilization has ever sustained. The gap between 163 kilometers per second, the best humanity has achieved, and 30,000 kilometers per second, the minimum needed for a nominally single lifetime mission, is a factor of approximately 184. The Parker Solar Probe needs to be about 184 times faster to reach the threshold of marginal single lifetime feasibility. This is not an incremental engineering improvement. In the history of space propulsion, moving from the first liquid-fueled rockets in the 1920s to the Saturn V that launched Apollo missions represented roughly a factor of 5 improvement in achievable mission velocity. Moving from chemical rockets to nuclear thermal propulsion, the most developed alternative would improve specific impulse by roughly a factor of 2, translating to modest improvements in mission velocity for similar mass ratios. The factor of 184 needed to reach one lifetime marginal feasibility to Proxima b is not a gap that any incremental development of existing propulsion technology can close. The rocket equation and Y chemistry cannot help. The most fundamental barrier to reaching Proxima b with any spacecraft derived from current technology is not the distance itself, but the physical relationship between propellant mass, exhaust velocity, and achievable final velocity described by the Tsiolkovsky rocket equation. This equation was published in 1903 by the Russian schoolteacher and theorist Konstantin Tsiolkovsky, and it has governed every rocket ever built since. Its form is simple. The change in velocity a rocket can achieve equals the exhaust velocity of its propellant multiplied by the natural logarithm of the ratio of the rocket's initial mass to its final mass. Simple in form, but brutal in consequence. The natural logarithm grows slowly. To achieve a velocity change equal to the exhaust velocity, you need a mass ratio of approximately 2.72, meaning the initial rocket weighs 2.72 times what it weighs after burning all its fuel. To achieve twice the exhaust velocity, you need a mass ratio of approximately 7.4. 3 times the exhaust velocity requires a mass ratio of about 20. 4 times requires a mass ratio of about 55. 5 times about 148. The fuel required to reach each additional multiple of exhaust velocity increases exponentially, while the velocity increment stays constant. This is the trap at the heart of rocket science, and it becomes catastrophic when the target velocity is many multiples of any achievable exhaust velocity. Chemical rockets, which combust propellants to produce high-temperature exhaust gases, are limited by the energy available in chemical bonds. The best chemical propellant combination available, liquid hydrogen burned with liquid oxygen, produces an exhaust velocity of approximately 4.4 kilometers per second in vacuum. This is the fundamental ceiling for chemical propulsion. It is set by the energy content of hydrogen-oxygen combustion, which cannot be increased by engineering improvements because it is determined by atomic physics. The Saturn V rocket, the most powerful launch vehicle ever successfully flown, had a mass ratio at launch of approximately 15. The rocket and its payload together weighed roughly 15 times what remained after all the propellant was burned. That ratio produced a payload in low Earth orbit. Getting to interplanetary space from there requires additional propellant stages. To achieve 10% of the speed of light, 30,000 kilometers per second, using chemical propulsion with an exhaust velocity of 4.4 kilometers per second, the required mass ratio is erased to the power of 6,818. The number E is approximately 2.718. E to the 6,818 power is a number so vast that it exceeds the number of atoms in the observable universe by an incomprehensibly large margin. Achieving 10% of light speed with chemical rockets is not merely impractical. It is physically impossible in the sense that the required propellant mass does not exist. There is not enough matter in the solar system to build the propellant supply that a chemically propelled spacecraft would need to reach 10% of light speed with any non-negligible payload. Even 1% of light speed, 3,000 kilometers per second, requires a chemical mass ratio of E to the power of 681, which is similarly beyond any physical resource. At this level of analysis, the problem of interstellar travel with chemical propulsion is not an engineering challenge. It is a mathematical certainty. Chemical rockets will never reach another star system with any meaningful payload. The only open question is what replaces them. Nuclear thermal propulsion, the most developed alternative to chemical rockets, heats a propellant, typically liquid hydrogen, by passing it through or near a nuclear fission reactor core. The energy available from nuclear fission is roughly 1,000,000 times greater per unit mass than the energy available from chemical combustion. But in nuclear thermal propulsion, the energy is used to heat propellant, rather than to provide thrust directly. The achievable exhaust velocity is limited by the maximum temperature the propellant can be heated to before it damages the reactor components, typically around 2,500 to 3,000 Kelvin for practical designs. This gives an exhaust velocity roughly twice that of chemical rockets, approximately 8 to 9 kilometers per second. An improvement, but the mass ratio required to reach even a tiny fraction of light speed remains far beyond any practical fuel supply. Nuclear thermal propulsion would allow fast emissions within the solar system, but does not change the fundamental impossibility of chemical scale propulsion for interstellar travel. Nuclear pulse propulsion, the concept studied as Project Orion in the late 1950s and early 1960s by physicists including Freeman Dyson and Ted Taylor, proposes using the detonation of nuclear explosive devices behind the spacecraft to provide propulsive thrust. The basic concept was validated in tabletop models, and serious engineering studies were conducted before the 1963 Partial Nuclear Test Ban Treaty effectively ended the program. Exhaust velocities in nuclear pulse designs could in principle reach 30,000 to 100,000 kilometers per second for some fusion-based variants, which would begin to approach fractions of a percent of light speed. But no nuclear pulse system has ever been built. The engineering challenges are immense, and even optimistic designs reach perhaps 3 to 5% of light speed after enormous fuel expenditure. It is one of the more seriously discussed concepts for early interstellar travel, but remains entirely theoretical and has never progressed past design studies. The energy wall that scales with velocity. Even setting aside the rocket equation and imagining propulsion systems that do not carry their fuel, the energy required to accelerate any significant mass to interstellar speeds is itself an obstacle that scales in an unforgiving way with velocity. Every kilogram of spacecraft mass that must be accelerated to a fraction of the speed of light requires a specific, calculable amount of kinetic energy. That energy must come from somewhere, must be generated by some physical process, and must be deliverable to the spacecraft in a form it can use for propulsion. At the speeds needed for interstellar travel, the energy requirements move well beyond what any known or near-future energy source can practically provide. At non-relativistic speeds, the kinetic energy of an object is 1/2 times its mass, times its velocity squared. A spacecraft of 1 metric ton, approximately the mass of a small car, travelling at 1% of the speed of light, carries kinetic energy of approximately 4.5 times 10 to the 16th joules. This is equivalent to roughly 10.5 megatons of TNT, comparable to a large thermonuclear weapon, contained in the kinetic motion of a 1-ton spacecraft. To accelerate the spacecraft from rest to this velocity requires delivering this much energy to it in a useful form. The total annual electricity generation of the United States is approximately 4.2 times 10 to the 18th joules. Accelerating a 1-ton spacecraft to 1% of light speed requires roughly 1% of the total annual US electricity production, delivered with perfect efficiency to the spacecraft's propulsion system. At 10% of the speed of light, the kinetic energy scales with the square of the velocity, increasing by a factor of 100. The same 1-ton spacecraft at 10% of light speed requires energy equivalent to the entire annual electricity production of the United States, applied with perfect efficiency. For a spacecraft large enough to carry human beings, life support, scientific instruments, radiation shielding, communications equipment, and spare parts for a multi-decade journey, the mass would be at minimum tens of thousands of metric tons. More realistically, hundreds of thousands. The energy requirement scales linearly with mass. Hundreds of thousands of tons of spacecraft at 10% of light speed require energy inputs that dwarf the entire current global energy production of human civilization. As velocities approach a significant fraction of the speed of light, relativistic effects must be included in the calculation, and they make the energy cost worse. The relativistic kinetic energy formula replaces the classical 1/2 mv squared with the full relativistic expression, which grows without bound as velocity approaches the speed of light. At 50% of light speed, the relativistic correction is significant. At 90% of light speed, the total kinetic energy is approximately 1.3 times the rest mass energy of the spacecraft, meaning the spacecraft would need to convert a mass comparable to its own total mass into pure energy to achieve this speed with perfect efficiency. At 99% of light speed, the kinetic energy is approximately 6 times the resty mass energy. The energy required to reach relativistic speeds is not merely impractical. It approaches and eventually exceeds the total energy content of the matter composing the spacecraft itself. The most efficient conceivable energy source for propulsion is matter-antimatter annihilation, which converts the combined mass of matter and antimatter entirely into energy, with a mass-to-energy efficiency of 100%, according to E equals mc squared. This is the theoretical upper limit of energy extraction from matter. No physical process can extract more energy from a given mass. Even with perfect matter-antimatter annihilation, the fuel mass required to accelerate a substantial spacecraft to 10% of light speed and decelerate it at the destination is significant, a substantial fraction of the spacecraft's dry mass. And antimatter does not exist in nature in usable quantities. all antimatter currently produced by human technology is created in particle accelerators at a cost of approximately $62 trillion per gram, produced at a rate of tens of nanograms per year globally. The quantity of antimatter needed for an interstellar mission would require energy inputs that no conceivable near-future civilization could provide, at production rates that are many orders of magnitude beyond current capability. Nor does antimatter solve the deeper problem that propulsion requires not only acceleration, but deceleration. A spacecraft traveling to another star is not useful if it arrives at its destination moving so fast that it crosses the entire planetary system in a matter of hours. Any mission intended to study planets, enter orbit, land probes, or support human activity must shed essentially the same amount of kinetic energy at arrival that it gained during departure. In energy terms, every interstellar mission contains two journeys, speeding up and slowing down. The energy requirements therefore do not end once cruise velocity is achieved. They must effectively be paid twice. This requirement is often hidden in simplified discussions of interstellar travel. Concepts such as laser sails, for example, avoid carrying onboard fuel during acceleration by using powerful laser arrays located in the solar system. The spacecraft rides the momentum of photons emitted by the laser system and gradually accelerates to high velocity. But once it reaches another star, the laser is billions of kilometers behind it. The destination system contains no corresponding laser array waiting to slow it down. Unless a separate braking mechanism exists, the spacecraft becomes a flyby mission rather than a mission capable of remaining at the target. Even the most optimistic concepts therefore exchange one difficulty for another. Nuclear fusion avoids some of the limitations of chemical propulsion, but requires reactors that have not yet been demonstrated even on Earth. Antimatter offers unmatched energy density, but demands manufacturing capabilities beyond anything currently imaginable. Laser propulsion removes onboard fuel, but creates infrastructure requirements on a planetary or stellar scale. Every proposed solution solves one problem while revealing another of comparable magnitude. The underlying reason is that energy requirements are not engineering inconveniences. They are direct consequences of conservation laws. The kinetic energy possessed by a spacecraft moving through space is a physically real quantity that must be supplied by some source and later removed by some process. No technological sophistication can make that energy disappear. Better engineering may reduce losses, improve efficiency, and optimize mission architecture, but it cannot alter the fundamental relationship between mass, velocity, and energy established by the laws of physics. This distinction is important because many technological challenges throughout history have eventually yielded to innovation. Crossing oceans, flying across continents, and reaching orbit all once appeared impossible or economically absurd. Interstellar travel is often assumed to belong to the same category, but the barriers discussed here are different in character. They are not merely questions of building stronger engines or lighter materials. They arise from the actual amount of energy required to move matter across interstellar distances within useful timescales. The universe does not care how advanced a civilization becomes. A spacecraft moving at a given speed possesses a specific amount of kinetic energy, and that energy must always be paid for in full. The deceleration problem. That doubles everything. A point that is systematically omitted from popular accounts of interstellar travel is that reaching another star system is only half of the propulsion problem. A spacecraft that arrives at Proxima b, traveling at 10% of the speed of light, will pass through the system in a matter of hours if it cannot decelerate. At 30,000 kilometers per second, a spacecraft crossing the Proxima Centauri system, which has a diameter perhaps comparable to our own solar system, would traverse the entire region in roughly 10 to 15 hours. There would be no time to achieve orbit around any planet, no possibility of landing, and no opportunity for sustained scientific observation of anything in the system. The probe would take photographs for a few hours and continue into the void beyond Proxima Centauri, never to return or be retrieved. For a flyby mission carrying only small instruments with no crew, this might be acceptable as a first step. But for any mission with the goal of actually studying Proxima b in detail, achieving orbit, deploying surface instruments, or landing human beings, the spacecraft must decelerate to speeds compatible with capture by the gravitational field of Proxima Centauri or its planet. This requires a deceleration maneuver with delta v, meaning velocity change comparable in magnitude to the cruise velocity. At 10% of light speed, decelerating to 0 relative to Proxima Centauri requires the same energy and propellant as accelerating to 10% of light speed in the first place. For a rocket carrying its own propellant for deceleration, the Tsiolkovsky equation must be applied twice, once for acceleration and once for deceleration. Because the propellant for deceleration must also be accelerated to cruise speed during the outbound journey, the total propellant mass increases multiplicatively rather than additively. If a mass ratio of 10 is required for the acceleration phase, and another mass ratio of 10 is required for the deceleration phase, the total mass ratio required for a stop-and-go mission is not 20, but 100. The exponential nature of the rocket equation makes combining acceleration and deceleration far more than twice as difficult as either phase alone. For the extreme mass ratios involved in any approach to interstellar speeds using known propellant types, the combined mission is not merely twice as hard, but many orders of magnitude harder than the one-way acceleration alone. Some proposed mission architectures avoid this problem by not carrying deceleration propellant from Earth. A magnetic sail, for example, could in principle interact with the charged particle wind of Proxima Centauri at the destination to provide braking force, using the stellar wind pressure itself as a brake. Laser light sails can be flipped after the cruise phase, so that the same laser beam that provided acceleration, now aimed at the front face of the sail after it has been turned around, can provide deceleration. These concepts are physically plausible in the same sense that many theoretical physics proposals are physically plausible. The underlying physics does not prohibit them. But the practical implementation of a laser able to focus a beam on a sail 4 light-years away with enough intensity to decelerate a spacecraft moving at a significant fraction of light speed requires engineering capabilities that are not merely beyond current technology, but are beyond any technology whose development path is clearly visible. The magnetic sail deceleration concept requires the sail to generate a sufficiently large effective cross-section for interaction with the stellar wind. At large distances from Proxima Centauri, the stellar wind is sparse. The braking force available from a magnetic sail interacting with a sparse stellar wind at the distances where deceleration would need to begin is constrained by the same physics that constrains other magnetic sail concepts, and calculations suggest that very large sail sizes, potentially kilometers in diameter, would be needed even for small spacecraft. Maintaining the structural integrity of a kilometre-scale magnetic sail structure through decades of interstellar transit, including impacts with interstellar medium particles at relativistic speeds, is an engineering problem with no current solution. Interstellar medium as an active threat. The space between the stars is not empty. This statement is physically accurate, but experientially counterintuitive, because the interstellar medium is so diffuse that in everyday terms it would be considered an extraordinarily good vacuum. In the local interstellar medium surrounding the solar system, the average particle density is approximately 1 atom per cubic centimetre, compared to roughly 27 quintillion molecules per cubic centimetre at sea level on Earth. In absolute terms, the interstellar medium is almost nothing. But almost nothing is not nothing, and the consequences of almost nothing become significant when the spacecraft crossing it is moving at a meaningful fraction of the speed of light. Kinetic energy scales with the square of velocity. A particle of mass m struck by a spacecraft moving at velocity v carries kinetic energy in the spacecraft's reference frame of 1/2 mv squared, which at 10% of light speed gives even a single hydrogen atom a kinetic energy of approximately 0.75 million electron volts. That is in the range of gamma radiation, a form of ionizing radiation capable of penetrating most shielding materials and depositing energy in any biological tissue or electronic component it passes through. The cumulative effect of encountering approximately 100 million hydrogen atoms per square centimetre per second of spacecraft frontal area, which is the expected flux at 10% of light speed through the local interstellar medium, produces a radiation environment that is extremely severe by any measure. Dust grains present a more acute mechanical hazard. The interstellar medium contains solid particles, primarily silicate and carbonaceous grains, at a density of approximately 1 particle per million cubic metres in typical conditions. These grains range in size from tens of nanometres to micrometres. A grain of mass approximately 1 microgram, which is a very small grain by any everyday standard, striking a spacecraft at 10% of the speed of light, carries kinetic energy of approximately 4.5 billion joules, equivalent to roughly 1 kiloton of TNT. A microgram grain delivering kiloton equivalent energy to a spacecraft structure would be catastrophic and would destroy any spacecraft not specifically designed to withstand such impacts. The breakthrough Starshot engineering studies, which represent the most detailed publicly available analysis of the interstellar medium hazard for small high-speed probes, estimated that a gram-scale chip travelling at 20% of the speed of light through the local interstellar medium would suffer significant erosion of its forward-facing surface from dust grain impacts. The estimated erosion depth over a 4 light-year journey was sufficient to destroy an unprotected silicon wafer. The proposed solution was a thin protective coating, but the coating material must itself survive the impacts without completely eroding away, must be manufacturable at the required thinness and quality, and must not compromise the chip's scientific payload or its ability to transmit data back to Earth. For a small chip, these engineering trade-offs are very difficult. For a large crewed spacecraft, the shielding mass required to protect the crew compartment against the interstellar medium particle flux at 10% of light speed would be substantial, adding significantly to the total mission mass and thereby increasing the energy and propellant requirements. The problem has no clean engineering solution. A thick shield protects but adds mass. A thin shield erodes. A shaped shield deflects some particles but not all. A magnetic shield deflects charged particles but not neutral ones, and most of the damaging large grains are neutral. Any interstellar mission architecture must account for decades of continuous exposure to this environment, and the cumulative damage over 4+ years of travel at relativistic speeds is not negligible for any material that has ever been tested. The interstellar medium is not simply empty space with a few inconvenient atoms. It is an active physical environment that imposes specific, calculable, severe constraints on any object attempting to cross it at high speed. The severity of this environment becomes clearer when the cumulative effects are considered over the entire duration of an interstellar voyage. A spacecraft travelling to Proxima Centauri at 10% of the speed of light would spend more than 40 years in continuous transit. Every second of that journey would expose its forward-facing surfaces to a relentless stream of energetic particles and occasional dust impacts. The damage is not a single catastrophic event, but a slow process of erosion, radiation exposure, and material fatigue, operating without interruption for decades. Radiation damage alone presents difficulties that extend far beyond ordinary spacecraft engineering. High-energy particles passing through structural materials can displace atoms from their positions within crystal lattices, gradually weakening metals, embrittling composites, and degrading electronic components. Modern spacecraft electronics are hardened against radiation, but they are designed for missions lasting years, not multiple decades of uninterrupted exposure in the interstellar medium. Memory corruption, transistor degradation, and cumulative electronic failures become increasingly likely as exposure accumulates. The challenge is particularly severe for any crewed mission. Human biology evolved under the protection of Earth's atmosphere and magnetic field. Outside that protective environment, energetic particles can damage DNA, increase cancer risk, impair the nervous system, and degrade cardiovascular health. Thick shielding reduces exposure but introduces another problem: mass. Every additional ton of shielding must itself be accelerated to interstellar velocity, increasing the mission's already enormous energy requirements. Thermal management also becomes difficult. Interstellar space is cold, but a fast-moving spacecraft continually absorbs energy from particle impacts and from the operation of its own systems. Excess heat must be radiated away through large radiator structures. Those radiators, however, are themselves exposed to erosion from dust impacts and radiation damage. A spacecraft must simultaneously protect itself from incoming energy while efficiently disposing of internally generated heat. Even communication becomes a survivability issue. A probe that suffers gradual antenna degradation, power system damage, or navigational sensor failures may successfully reach its destination yet be unable to transmit meaningful data back to Earth. The mission could technically succeed while humanity receives little or no information from it. Taken together, these factors reveal that interstellar travel is not simply a propulsion problem. Achieving the required speed is only the beginning. The spacecraft must then survive an environment that continuously attacks its structure, electronics, communication systems, and potentially its crew for decades without maintenance, repair facilities, or rescue. The interstellar medium is sparse, but over the immense distances between stars, even sparsity becomes a powerful obstacle. Cosmic radiation and the biological limit. Human beings are biological organisms whose continued function depends on maintaining the integrity of their cellular machinery, particularly their DNA. Ionizing radiation, which includes high-energy photons like X-rays and gamma rays, as well as charged particles like protons, electrons, and heavy nuclei, damages DNA through direct ionization of the molecular bonds and through the production of reactive free radicals that subsequently attack DNA. The body has repair mechanisms for moderate levels of radiation damage, but these mechanisms can be overwhelmed at high doses, leading to acute radiation syndrome, increased cancer risk, and in severe cases death. The galactic cosmic ray environment in interstellar space is significantly more severe than the environment within the solar system. Inside the solar system, the heliosphere, the bubble of solar wind and magnetic field that the Sun projects outward, provides substantial shielding against lower energy galactic cosmic rays. Beyond the heliopause, where Voyager 1 now travels, this shielding is absent, and the full galactic cosmic ray spectrum is present. Galactic cosmic rays originate from astrophysical acceleration processes, primarily supernova remnants, and span a range of energies from millions to billions of electron volts per nucleon. At the high energy end, they include heavy nuclei, iron and nickel nuclei stripped of all their electrons and accelerated to nearly the speed of light, which are particularly damaging because a single heavy nucleus travelling through biological tissue deposits its energy along a narrow track, causing dense local ionization that overwhelms local repair mechanisms. NASA has studied the radiation environment for potential Mars missions, which would require roughly 6 months each way in deep space outside the heliosphere, plus time on the Martian surface, which has minimal atmospheric shielding. The estimated lifetime radiation dose for a typical Mars mission exceeds the career exposure limits established for NASA astronauts for low Earth orbit missions. For a mission to Proxima b lasting a minimum of 42 years at 10% of light speed, the galactic cosmic ray exposure would be approximately 100 times greater than a Mars mission, not accounting for the additional radiation produced by the spacecraft's own motion through the interstellar medium at relativistic speeds. At relativistic speeds, the spacecraft's motion adds an effective radiation field that does not exist for slow-moving spacecraft. In the reference frame of the spacecraft, the hydrogen atoms of the interstellar medium are not simply sitting there. They are approaching at nearly 10% of the speed of light and strike the forward face of the spacecraft with enough energy to produce secondary particle showers, cascades of additional particles created by the initial impact. These secondary showers include pions, muons, neutrons, and gamma rays that penetrate further into the spacecraft structure than the initial proton impact would. The crew compartment of a crewed spacecraft would need to be shielded against this secondary particle background in addition to the direct galactic cosmic ray flux, requiring shielding mass that is difficult to reconcile with the mission's energy and propellant constraints. The biological problem has no engineering solution that does not impose enormous mass penalties. Adequate shielding against the galactic cosmic ray environment during a 40-year interstellar transit requires a shield areal density, the mass of shielding material per unit area that exceeds what any mission architecture has proposed without incurring mass penalties that make the mission energy requirements even more extreme. The alternative of not shielding adequately and accepting the biological consequences is not viable for a crewed mission. Crew members exposed to the estimated radiation environment of a 4 light-year transit at 10% of light speed would likely suffer radiation doses many times the established limits for increased cancer risk within the first few years of the journey, with cumulative health consequences that would compromise the crew's ability to function by arrival. Some proposed solutions attempt to reduce the biological burden rather than eliminate the radiation itself. One frequently discussed concept is induced hibernation or suspended metabolism, in which crew members spend most of the journey in a low metabolic state. This approach could reduce life support requirements and perhaps lessen certain physiological effects of long-duration spaceflight, but it does not solve the radiation problem. DNA damage accumulates whether a person is awake or asleep. A sleeping cell struck by a high-energy ion nucleus is damaged just as effectively as an active one. More speculative proposals involve advanced biological engineering. Future civilizations might develop genetic modifications that improve DNA repair mechanisms, increase resistance to radiation-induced cancer, or replace particularly vulnerable biological systems with artificial alternatives. Such approaches remain hypothetical and introduce their own uncertainties. Biological systems are extraordinarily complex, and modifications that improve resistance to one form of damage often create vulnerabilities elsewhere. No organism known today is capable of tolerating the cumulative radiation exposure expected during a decades-long interstellar voyage at relativistic speeds. The problem becomes even more severe when mission reliability is considered. Radiation does not merely threaten crew health, it threatens the mission itself. Cognitive impairment, increased cancer incidence, cardiovascular damage, cataracts, and immune system dysfunction all become more likely as cumulative dose increases. Even if a crew survives physically, maintaining the level of performance required to operate a spacecraft for 40 years, conduct scientific investigations, manage emergencies, and establish a functioning presence at the destination becomes increasingly difficult under chronic radiation exposure. This is what makes radiation one of the most fundamental barriers to human interstellar travel. Propulsion can, in principle, be improved. Travel times can be shortened by higher velocities. But every increase in velocity tends to worsen the radiation environment by increasing the energy of interstellar particle impacts. The challenge is therefore not isolated, but interconnected with every other major obstacle. The faster a spacecraft travels, the greater the shielding requirements become. The greater the shielding requirements, the larger the spacecraft mass becomes. The larger the mass, the greater the energy required for propulsion. Radiation is not merely one problem among many. It is woven into the entire architecture of interstellar travel, linking biology, engineering, and physics into a single constraint that no current technology can overcome: time and civilizational continuity. Beyond the physical challenges of propulsion, shielding, and the interstellar medium lies a category of obstacle that is rarely addressed in technical discussions of interstellar travel, but may be among the most severe: the challenge of maintaining the institutional, social, and technological infrastructure needed to support a mission across timescales that exceed the documented persistence of any human organization. The fastest physically plausible mission to Proxima b using near-future technology is commonly discussed in the context of 10% of light speed, which gives a transit time of approximately 42 years, not including acceleration and deceleration. 42 years is within a human lifetime. A person who began working on such a mission at age 25 could in principle live to receive the first signals from the destination. This is the most optimistic serious timeline, and it requires propulsion technology that does not currently exist and whose development path is not clear. Slower missions, using technologies that are somewhat more proximate to current capability, would require hundreds to thousands of years. A mission at 1% of light speed requires approximately 420 years. At 0.1% of light speed, the transit takes 4,200 years. These timescales are not merely long in the sense that a person would not survive them. They are long in the sense that no human institution has ever survived them in recognizable form. The Catholic Church, one of the oldest continuously operating institutions in the Western world, has existed for roughly 2,000 years. But the institution of 2025 is not recognizably the same as the institution of 25 CE in its organizational structure, its doctrine, its geographic center, its relationship to political authority, or its cultural character. The institution persists in name, while the entity it describes has transformed fundamentally. A mission architecture that requires 400 years of continuous support from a sponsoring civilization assumes that the civilization will maintain, over that period, the technological capability to receive and decode the signals, the institutional memory to know what the signals mean and what the mission was, the cultural priority to continue caring about the mission's outcome, and the infrastructure to act on whatever information is received. None of these assumptions has historical precedent on the relevant timescales. Human technological civilizations have demonstrably lost capabilities that they once possessed. The technology for making Roman concrete was lost for roughly 1,500 years. The technology for constructing the Antikythera mechanism, a sophisticated astronomical calculator, was apparently not transmitted to successor civilizations. In both cases, the lost knowledge was eventually recovered or independently reinvented. But the intermediate period of loss represents exactly the kind of institutional discontinuity that could interrupt a multi-century interstellar mission. The generation ship concept addresses the biological problem of individual lifespans by proposing a spacecraft large enough to house a self-reproducing population across multiple generations. The crew who launches the mission is not the crew who arrives. Their descendants, born and raised aboard the ship, complete the journey. This concept has been discussed seriously by space engineers and theorists and has attracted sustained speculative attention in the scientific community. The engineering requirements are specific. The ship must sustain a biosphere, an agricultural system, a manufacturing capability, a medical system, an educational system, and a governance structure for the duration of the mission, which might span 15 to 20 human generations at a minimum for a transit to Proxima b at realistically achievable speeds. No closed ecological system of the complexity needed to support a multi-generational human population has ever been successfully sustained. Biosphere 2, a large closed ecological experiment conducted in Arizona in the early 1990s, housed 8 people in a sealed facility covering roughly 1.27 hectares for 2 years. The experiment experienced significant problems with oxygen depletion, agricultural failures, and ecological collapse of several of its designed systems. It required external intervention to address oxygen levels dropping to concentrations that threatened the health of the participants. A generation ship would need to maintain its biosphere for not 2 years, but 400 to 4,000 years without external intervention of any kind, because the communication delay makes real-time assistance impossible, and any physical resupply is out of the question. The destination's uncertainty. What we do and don't know. Every challenge discussed so far is a challenge on the journey. The destination presents its own category of problems, which are not engineering problems in the conventional sense, but rather problems of knowledge. The specific, documented things we do not know about Proxima b that are directly relevant to whether arriving there constitutes reaching a second potentially habitable world, or constitutes arriving at a place that is inhospitable in ways that make the entire journey's scientific premise questionable. Proxima b was confirmed as a planet in 2016 based on radial velocity observations that detected a periodic oscillation in the velocity of Proxima Centauri consistent with the gravitational pull of a planet with a minimum mass of approximately 1.07 Earth masses orbiting at a distance of 0.0485 astronomical units with an orbital period of 11.2 days. These facts are established. They place Proxima b in the circumstellar habitable zone of Proxima Centauri, where if the planet has an atmosphere with appropriate greenhouse properties, surface temperatures could allow liquid water. This is the observational basis for the description of Proxima b as potentially habitable. What is not known about Proxima b fills several categories of scientific uncertainty that are not minor gaps in knowledge, but fundamental questions about whether the planet is anything like what the phrase potentially habitable implies. First, the planet's radius is unknown. The radial velocity method detects the gravitational pull of a planet on its star, but does not detect the planet's size directly. Proxima b has not been observed in transit, meaning it has not been seen passing in front of its star in a way that would allow its radius to be measured from the fractional dimming it causes. Without a radius measurement, the planet's density cannot be calculated, and without density, its composition remains uncertain. Proxima b's minimum mass of 1.07 Earth masses is consistent with a rocky planet similar to Earth, but it is also consistent with a planet much larger than Earth if its orbital inclination is such that the measured radial velocity signal represents only a fraction of the planet's true orbital velocity. A more massive planet with a lower density composition, an ocean world, a mini-Neptune, would have very different surface conditions from a rocky Earth analogue. Second, Proxima b's atmosphere, if it has one, is entirely unconstrained by current observation. An atmosphere is the single most important factor determining whether the planet's surface could support liquid water. Without an atmosphere, the surface temperature on the sunlit side of a tidally locked planet would be determined by the direct stellar flux, which for Proxima b's orbital distance would produce surface temperatures on the day side significantly above the boiling point of water and on the night side near absolute zero. With a thick CO2 atmosphere, greenhouse warming could maintain liquid water across a larger surface fraction. With an Earth-like nitrogen-oxygen atmosphere, different dynamics would apply. With no atmosphere at all, there is no habitability to speak of. Proxima Centauri is a flare star. It produces energetic flares of ultraviolet and X-ray radiation far more frequently than the Sun does, and the flux of these flares at Proxima b's very close orbital distance is orders of magnitude higher than the solar UV and X-ray flux Earth receives. The ability of any atmosphere to survive the stripping effect of Proxima Centauri's particle wind and flare radiation over billions of years depends on the planet's magnetic field, its initial atmospheric inventory, and the rate of atmospheric resupply from geological outgassing. Models of these processes give a range of outcomes from a completely stripped airless body to a thick atmosphere sustained by active geology, with the actual outcome depending on parameters that observations have not yet constrained. The question of tidal locking further complicates the habitability picture. At Proxima b's orbital distance and with a star of Proxima Centauri's mass, the tidal circularization and synchronization timescales are sufficiently short that the planet is expected to have reached tidal synchronization within the age of the system, resulting in one hemisphere permanently facing the star in perpetual daylight and the other in permanent darkness. The dynamics of a tidally locked planet's climate depend critically on whether a functioning atmosphere can transport heat from the day side to the night side efficiently enough to prevent the night side from trapping so much of the atmospheric gases as surface ice that the remaining atmospheric mass is too thin to sustain meaningful greenhouse warming. This is the collapse scenario, and its prevention requires atmospheric conditions that current models can neither confirm nor rule out for Proxima b. The communication delay that makes every mission worse. One of the least discussed but most operationally significant consequences of Proxima b's distance is the communication delay between the spacecraft and Earth. At the speed of light, a signal from Proxima Centauri takes 4.24 years to reach Earth. A response takes another 4.24 years to return. The minimum round-trip communication time between a spacecraft at Proxima b and mission control on Earth is approximately 8.5 years. No command sent from Earth can influence events at the spacecraft for 4.25 years after it is transmitted, and no information about events at the spacecraft can influence decisions on Earth until 4.25 years after those events occurred. This communication delay has specific, severe consequences for any mission architecture. Every anomaly, every system failure, every unexpected scientific discovery, every emergency must be handled entirely autonomously by the spacecraft or its crew, because Earth-based mission control cannot respond in any useful time frame. The two-way delay that makes teleoperation of Mars rovers already difficult, ranging from 3 to 22 minutes each way, depending on orbital geometry, would be expanded by a factor of roughly 1200 at Proxima b. Mission Control could observe an emergency on the spacecraft, craft a response, transmit it, and receive confirmation that the response was received and implemented over a period of more than 8 years. Any emergency requiring a response in less than 4 years must be handled without Earth's involvement. For a crewed mission, this means the crew must be capable of independently diagnosing and resolving every possible medical emergency, every mechanical failure, every computer malfunction, every life support system anomaly, and every scientific question that arises during the transit and the time at the destination, without real-time support from Earth. The crew must carry all the knowledge, tools and spare parts needed to address any conceivable problem, because requesting additional resources or expertise from Earth and receiving a response would take nearly a decade. The depth and breadth of expertise required from a crew that can fully self-sufficiently operate a spacecraft, conduct scientific investigations, maintain their health and psychological stability, and handle any emergency across a 40-plus year mission without meaningful real-time contact with Earth is without precedent in human history. For an unmanned probe, the communication delay means that the scientific mission must be planned in advance with all possible contingencies anticipated, because no mid-mission course corrections based on early discoveries can be implemented within any time frame short of 8 years. A probe that reaches Proxima b and discovers an unexpected feature in the planetary system cannot relay that discovery to Earth for 4 years and cannot receive instructions about how to respond to it for another 4. Scientific missions to the outer solar system already grapple with communication delays of hours to days, and those missions require careful autonomous operation protocols. A communication delay measured in years instead of hours creates a qualitatively different mission planning challenge that cannot be addressed simply by writing better software. It requires the spacecraft to be capable of fully autonomous, flexible scientific investigation without any human guidance, a level of artificial general intelligence capability that does not currently exist. The communication problem extends beyond emergency response and scientific operations into something more fundamental: the maintenance of a shared reality between the spacecraft and Earth. Human institutions function through continuous feedback. Governments receive information about changing conditions and adapt. Scientific communities exchange data, critique one another's conclusions, and refine their understanding. Families maintain relationships through regular communication. Every complex social system depends on information moving through it quickly enough that decisions remain connected to current circumstances. At Proxima b distances, that connection breaks down. A crew arriving in the Proxima system would be living in a reality that Earth could not observe until more than 4 years later. Likewise, the crew would make decisions based on information about Earth that was already 4 years out of date. Any conversation between the two worlds would unfold on a timescale measured not in minutes, days, or even months, but in decades. Consider a simple exchange. A crew detects something unexpected in the Proxima system and sends a detailed report to Earth. 4 years and 3 months later, the message arrives. Scientists on Earth spend several months analysing the data and preparing recommendations. The reply takes another 4 years and 3 months to reach the spacecraft. By the time the crew receives Earth's response, nearly 9 years have passed since the original observation. Entire phases of the mission may have ended. Equipment may have failed. The spacecraft may have moved to a different target. Crew members may have retired from operational roles or died. The recommendation could arrive after the circumstances it was designed to address have ceased to exist. This temporal separation effectively transforms the spacecraft into an independent civilization. Even if it remains politically and culturally connected to Earth, operationally it must function as a self-governing entity. Every major decision must be made locally because the communication delay prevents meaningful external oversight. Mission planners can write procedures, establish priorities, and define objectives before launch, but they cannot continuously direct events once the spacecraft is beyond the reach of rapid communication. The problem becomes even more severe for missions lasting multiple decades. Human societies change rapidly on historical timescales. The 42 years required to reach Proxima b at 10% of light speed is longer than the period between the invention of the World Wide Web and the present day. A spacecraft departing Earth in one technological era may arrive during another entirely different era. Scientific knowledge accumulated on Earth during the voyage could radically exceed what was available at launch. Entire fields of study may emerge, new propulsion systems, new communication technologies, or new understandings of biology and physics may be developed while the spacecraft is still en route. The crew, however, remains tied to the technological assumptions of the launch period. They cannot upgrade their spacecraft with inventions that have not yet reached them. They cannot instantly access discoveries made decades after departure. Even if Earth transmits every new breakthrough, the information itself arrives years after it was generated. The spacecraft effectively becomes a technological time capsule, carrying the capabilities and assumptions of an earlier era into the future. This raises a paradoxical possibility. A mission launched at enormous expense and effort could become technologically obsolete before it arrives. A propulsion breakthrough developed 20 years after launch might enable a second spacecraft to complete the same journey more efficiently. A new observational technology might allow Earth-based astronomers to gather much of the desired scientific data remotely. The original mission would continue because it cannot be recalled, but its justification could be transformed by developments occurring entirely beyond its control. For robotic missions, advances in artificial intelligence offer a partial solution. A sufficiently capable autonomous system could identify scientific opportunities, adapt to unexpected conditions, and make complex decisions without waiting years for instructions from Earth. Yet this solution introduces its own uncertainties. The more autonomy granted to the system, the less direct control mission planners retain. A probe sophisticated enough to function independently for decades in an alien planetary system would need decision-making capabilities far beyond those demonstrated by any existing spacecraft. Current planetary probes operate according to carefully designed procedures and decision trees. They can handle anticipated situations and perform limited autonomous adjustments. They do not formulate scientific theories, redesign mission objectives, or creatively respond to entirely novel phenomena. An interstellar probe would likely need some version of those capabilities. It would have to determine which observations are most valuable, allocate limited resources accordingly, and respond to discoveries that mission designers could not predict decades earlier. The communication delay also affects the psychological dimensions of exploration. Exploration has traditionally involved a continuous connection between explorers and the societies that sent them. Sailors crossing oceans could eventually return. Polar expeditions could communicate through support networks. Astronauts aboard the International Space Station remain in near constant contact with Earth. Even Mars astronauts would experience delays measured in minutes rather than years. A Proxima mission would be fundamentally different. Crew members would spend decades separated from real-time human contact. Births, deaths, political changes, cultural shifts, and scientific revolutions on Earth would all reach them years after the fact. Relationships with friends and family would become asynchronous exchanges stretched across nearly a decade for every complete conversation. The emotional consequences of such isolation are difficult to predict because no human population has ever experienced communication delays of this magnitude while remaining connected to its society of origin. Ultimately, the communication challenge illustrates a broader truth about interstellar travel. Distance is not merely a problem of transportation, it is a problem of information. The speed of light limits not only how quickly spacecraft can move, but how quickly knowledge itself can travel. A civilization attempting to reach another star system must confront the reality that physical separation and informational separation grow together. The farther a mission travels, the more independent it becomes, until eventually the distinction between an expedition and a separate civilization begins to blur. Even if propulsion, radiation shielding, life support, and all the other engineering obstacles could somehow be solved, the communication delay would remain. It is not a technological limitation, but a consequence of the geometry of space-time itself. 4 light years means 4 years for a message. No amount of better engineering changes that. Any mission to Proxima b must therefore accept a reality unlike anything in previous exploration. A journey so distant that the explorers and the civilization that launched them cease to share the same present. What Breakthrough Starshot actually proposes and what it does not. Breakthrough Starshot is the most extensively publicized and most technically developed proposal for sending any human-made object to another star system within a time frame measured in decades rather than millennia. Announced in April 2016 with backing from physicist Stephen Hawking, entrepreneur Yuri Milner, and Facebook founder Mark Zuckerberg, it attracted significant scientific attention and $100 million in initial funding for research and development. It represents the most serious contemporary effort to move interstellar travel from theoretical speculation to engineering planning, and examining what it actually proposes and what it explicitly does not propose is essential for understanding the realistic state of interstellar capability as it currently exists. Breakthrough Starshot proposes to send gram-scale probes to Alpha Centauri, the broader stellar system that includes Proxima Centauri, at approximately 20% of the speed of light, enabling an arrival within roughly 20 years of launch. The probes would be centimetre-scale chips carrying a camera, navigation system, communication laser, and minimal scientific instruments, all integrated onto a wafer of silicon weighing approximately 1 gram. Each chip would be attached to a light sail, a thin reflective surface measuring roughly 4 meters on a side, weighing a total of a few grams. The acceleration would be provided by an array of ground-based lasers with a combined output of approximately 100 gigawatts, focused on the sail for approximately 10 minutes during the departure phase. The concentrated laser pressure on the sail would accelerate the combined chip and sail system to 20% of light speed within that 10-minute window. The probes would then coast to Alpha Centauri with no further propulsion, requiring no onboard fuel at all. Upon arrival, they would collect data for a few hours while passing through the system at 20% of light speed and transmit what they find back to Earth using an onboard laser. The signal would take approximately 4 years to arrive. This concept is physically coherent. None of the steps violates known physics. The pressure of light on a reflective surface is a real phenomenon described by Maxwell's equations and confirmed experimentally. Accelerating a very small, very light object to high velocities with concentrated laser light is physically achievable in principle. The concept has enough physical validity that serious physicists and engineers have engaged with it in technical detail, and the Breakthrough Starshot team has published analyses of specific engineering challenges rather than simply asserting the concept is feasible. The engineering challenges that have been identified are severe, and they explain why the project has been placed on indefinite hold as of 2025, having spent only approximately $4.5 million of its $100 million budget over nearly a decade of preliminary research. The laser array required is approximately 100 gigawatts of coherent laser output, roughly equivalent to the total electrical generating capacity of a country the size of France, focused on a target measuring 4 meters across at a distance that grows from 0 to several thousand kilometers during the 10-minute acceleration phase. Maintaining the coherent phase alignment of a distributed laser array over the needed output range while tracking an accelerating target is an optical engineering problem of extraordinary difficulty. The sail must be designed to reflect nearly all incident laser power, because absorbing even a small fraction of 100 gigawatts of laser light would vaporize any known material almost instantaneously. The required reflectivity exceeds what any current engineered surface achieves at the needed power density, and developing a material that meets this requirement while remaining strong enough to withstand the acceleration forces is an unsolved materials science problem. The chip must survive the acceleration phase, during which it experiences forces of approximately 10,000 times Earth's gravitational acceleration for approximately 10 minutes. It must then survive 4 years of transit through the interstellar medium at 20% of light speed, where the particle radiation environment is extremely severe, and where even small dust grains represent a potentially mission-ending impact hazard. It must arrive at Proxima Centauri with enough power remaining in its onboard source to operate its camera and transmit data back to Earth using a laser no larger than what can fit on a centimetre scale chip. The transmission must be powerful enough and well enough directed to be detectable by receivers on Earth after travelling 4.24 light-years. Even accepting that all of these engineering challenges could eventually be resolved, the breakthrough starshot concept does not propose sending humans to Proxima b. It does not propose sending a probe that can orbit the planet or land on it. It proposes sending a chip the size of a postage stamp that will fly through the system at 20% of light speed, taking photographs and measurements for a few hours, and then continuing into the void beyond. The scientific return from such a mission would be immensely valuable as an initial characterization of the nearest stellar system. It would not constitute reaching Proxima b in any sense that includes sustained presence, exploration, or human contact with the world. The gap between a postage stamp chip flying past a planet at 60,000 kilometers per second and a crewed mission establishing a scientific presence there is as large as the gap between any current technology and breakthrough starshot itself. Fusion propulsion, the promise and the timeline problem. Nuclear fusion, the process that powers the Sun and all other stars, has been the subject of sustained scientific and engineering effort for human energy production since the 1950s. The potential energy density of fusion reactions is approximately 4 million times that of chemical combustion reactions on a per kilogram of fuel basis, and fusion reactors would produce far less long-lived radioactive waste than fission reactors. The standard joke in the field, that practical fusion power has been 30 years away for the past 70 years, reflects a real history of technical difficulty that has repeatedly pushed the commercialization of fusion energy beyond the horizon of immediate feasibility. The relevance of fusion to interstellar propulsion depends entirely on when and whether sustained controlled fusion becomes an engineering reality rather than a laboratory demonstration. In 2022, the National Ignition Facility at Lawrence Livermore National Laboratory achieved fusion ignition for the first time, producing more energy from a fusion reaction than the laser energy delivered to the target. This was a genuine scientific milestone, confirming that controlled inertial confinement fusion can produce net energy in the sense of the reaction producing more than the energy deposited in the fuel capsule by the lasers. It was subsequently replicated and improved in follow-on experiments in 2023. The achievement was real and significant. It does not, however, mean that fusion power plants are imminent or that fusion propulsion for spacecraft is near. The 2022 experiment produced approximately 3 megajoules of fusion energy from approximately 2 megajoules of laser energy delivered to the target. The lasers themselves required approximately 300 megajoules of electrical energy to operate, meaning the overall wall plug efficiency of the system was approximately 1%. A power plant based on this technology would need to improve efficiency by at least a factor of 50 to be economically viable as an energy source, and that improvement has not been achieved. For propulsion applications, a fusion engine must not merely produce net energy, but must convert that energy into directed thrust with high efficiency, and must do so in a compact, lightweight, and reliable package that can operate continuously for decades in the environment of space. None of the current fusion concepts, including the various magnetic confinement approaches like tokamaks, the inertial confinement approach used at the National Ignition Facility, or the field reverse configuration approaches being developed by private companies, has been demonstrated to work in a form compatible with spacecraft propulsion. The engineering path from a laboratory demonstration of fusion ignition to a space-qualified fusion propulsion system is a very long one, involving challenges of miniaturization, thermal management, reliability, and operational lifetime that are qualitatively different from the challenges of achieving ignition itself. The most thoroughly designed fusion propulsion concept for interstellar travel is Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s. The Daedalus design used pellet-driven inertial confinement fusion igniting small pellets of deuterium and helium-3 with electron beams to produce thrust. The design called for a two-stage vehicle weighing approximately 54,000 tons, of which approximately 50,000 tons was fuel, and projected a cruise velocity of approximately 12% of the speed of light. At that speed, a mission to Barnard's star, roughly 6 light-years away, would take approximately 50 years. The design was explicitly a flyby mission with no deceleration, because carrying enough fuel to decelerate at the destination would have required a vehicle mass that the study found impractical even by the generous assumptions already built into the design. The Daedalus study identified several critical dependencies that have not been resolved in the nearly 50 years since the study was conducted. The most acute is the fuel supply. The design required approximately 30,000 tons of helium-3, an isotope that is essentially absent from Earth in useful quantities. The only identified source of helium-3 in the amounts needed was the atmosphere of Jupiter, requiring a dedicated industrial-scale extraction program in Jupiter's atmosphere, which is itself a technological challenge far beyond current capability. The assumption that any civilization able to build Daedalus would also be able to mine Jupiter's atmosphere for helium-3 may be correct in a very long time frame, but it places the Daedalus-class mission in a category of technology that is not merely 50 or 100 years away, but potentially centuries away, conditional on the development of a complete interplanetary industrial infrastructure that does not currently exist in any form. The private fusion companies that have attracted substantial investment in recent years, including Commonwealth Fusion Systems, TAE Technologies, Helion Energy, and others, are focused on terrestrial power generation, not propulsion. Their timelines for achieving practical fusion power range from the late 2020s to the 2040s in the most optimistic projections. Adapting any of these technologies to spacecraft propulsion, even if the terrestrial power generation problem is solved, would require additional decades of engineering development. A fusion propulsion system capable of accelerating a spacecraft to 10% of light speed is not a near-term prospect by any analysis, and the specific energy densities and thrust-to-weight ratios required for an interstellar mission are significantly more demanding than those needed for a terrestrial power plant, or even for an in-system spacecraft. Antimatter, the physics of the perfect fuel and why we cannot make it. Antimatter annihilation is the most energy-dense reaction known to physics. When a particle of matter meets its antimatter counterpart, both are completely converted into energy according to Einstein's E equals mc squared, with 100% conversion efficiency. By comparison, nuclear fission converts approximately 0.1% of fuel mass to energy, and fusion converts approximately 0.7%. Chemical combustion converts approximately 1 part in 2 billion of fuel mass to energy. Antimatter annihilation converts 100%, making it theoretically 1,000,000 times more energy dense than fusion and 1,000,000,000 times more energy dense than chemical combustion. If antimatter fuel could be produced and stored in quantity, a spacecraft using matter-antimatter annihilation as its energy source would have a significant advantage over any other propulsion concept in terms of the ratio of energy available to fuel mass. The fundamental problem is not physical, but chemical and economic. Antimatter does not exist in nature in accessible form. The observable universe contains overwhelming, predominantly matter, with antimatter present only in trace quantities produced by high-energy astrophysical processes and decaying almost immediately. To produce antimatter artificially, it must be created in particle accelerators, facilities that use enormous electrical energy inputs to accelerate particles to very high energies and collide them to produce particle-antiparticle pairs. The process is extraordinarily inefficient. The Fermi National Accelerator Laboratory and CERN The world's most capable particle physics facilities produce antimatter in quantities measured in nanograms per year, at an effective cost estimated between tens of trillions and a quadrillion dollars per gram, depending on the accounting method. To fuel a spacecraft capable of reaching even 1% of the speed of light using matter-antimatter annihilation, several tons of antimatter would be needed, depending on the spacecraft's total mass and the efficiency of the propulsion system. Producing several tons of antimatter at current production rates and costs is not a problem that scales. It would require more energy than the Sun produces in billions of years, and more money than the global economy has produced in all of recorded history, at current production efficiencies. Even if the efficiency of antimatter production could be improved by 10 orders of magnitude, the energy required to produce mission-relevant quantities would still exceed global energy production capacity by many orders of magnitude. The storage problem is equally severe. Antimatter annihilates upon contact with ordinary matter, releasing energy. Storing significant quantities of antimatter requires maintaining it in complete isolation from ordinary matter, which in practice means magnetic or electric field confinement in a perfect vacuum. Current penning traps, the best available technology for containing charged antimatter particles, can hold approximately 10 billion antiprotons at a time, a quantity so small that it is effectively unmeasurable by mass. Scaling these devices to hold tons of antihydrogen, the most energetically useful form of antimatter for propulsion, while maintaining the required vacuum integrity and magnetic field strength over the decades of an interstellar transit, is not an engineering problem with an identifiable solution path. A single failure of the containment system would release the stored antimatter energy with catastrophic consequences for the spacecraft. A 2012 NASA-funded study on antimatter propulsion estimated that the minimum amount of antimatter needed for a one-way mission to Alpha Centauri using a fusion antimatter hybrid engine was approximately grams to kilograms, depending on the mission architecture, far less than the tons required for a pure antimatter rocket. Even at this reduced requirement, producing grams of antimatter would require energy inputs and costs that dwarf the entire Apollo program and the entire current annual budget of NASA, at production efficiencies orders of magnitude better than anything currently demonstrated. The study concluded that antimatter propulsion, while physically compelling, is not a near-term or even medium-term option for any actual mission. It belongs in the category of technology that would require not merely engineering development, but a qualitative transformation in human energy production and management capability that has no identified development timeline. There is also a deeper limitation that is often overlooked when antimatter propulsion is discussed. Antimatter does not eliminate the energy requirements of interstellar travel. It merely changes where that energy is stored. Every joule released by antimatter annihilation must first be invested in creating the antimatter itself. Antimatter is therefore not an energy source in the conventional sense, but an energy storage medium, analogous to a battery. A spacecraft powered by antimatter is ultimately powered by whatever civilization-scale energy infrastructure was used to manufacture the antimatter before launch. Even if future technologies dramatically improve production efficiency, the thermodynamic accounting cannot be escaped. Producing a kilogram of antimatter requires at least the equivalent energy contained in that kilogram's rest mass, approximately 9 × 10⁻16 joules, before any inefficiencies are considered. Real systems would require substantially more. A civilization capable of manufacturing the quantities of antimatter needed for interstellar missions would therefore already possess energy generation capabilities on a scale far beyond anything humanity currently operates. This places antimatter propulsion in a unique category. Unlike chemical rockets, nuclear fission, or even fusion concepts, its feasibility depends less on advances in propulsion engineering and more on advances in energy production, storage, and industrial infrastructure. The challenge is not discovering how to use antimatter. The physics of matter-antimatter annihilation is already understood with extraordinary precision. The challenge is acquiring enough antimatter to matter. Until a civilization can routinely generate and manage energy on scales vastly exceeding those of present-day humanity, antimatter propulsion remains less a practical engineering project than a benchmark for what a truly advanced technological society might someday be capable of attempting. Light sails and laser propulsion, the most credible near-term path. Among all the propulsion concepts proposed for interstellar travel, laser-driven light sails are currently the most seriously discussed in terms of near-term physical feasibility, primarily because they decouple the energy source from the spacecraft itself. Conventional rockets must carry their fuel, which means the mass of fuel must itself be accelerated along with the payload, creating the exponential mass ratio penalty of the Tsiolkovsky equation. A light sail carries no fuel. Its acceleration is provided entirely by photon pressure from an external source, typically a high-powered laser or laser array, based near Earth or in Earth orbit. The spacecraft's mass is limited to the sail itself and whatever scientific payload it carries without any propellant mass penalty. The physics of light sail propulsion are straightforward and well established. Photons carry momentum despite having no rest mass, and when a photon is reflected by a surface, it transfers twice its momentum to that surface. A sufficiently large sail with a sufficiently high reflectivity, illuminated by a sufficiently powerful laser, experiences a calculable acceleration. For a small sail and a very large laser, the acceleration can in principle be substantial. The breakthrough starshot concept described in Chapter 11 is specifically a laser sail concept scaled to its most ambitious near-term form. A gram-scale payload, a square-meter class sail, and a gigawatt-class laser array. The concept is not new. The idea of using radiation pressure from sunlight to propel spacecraft without any laser at all was proposed by the Soviet scientist Friedrich Sander in the 1920s. Solar sailing has been demonstrated in space. The Japanese Ikaros spacecraft, launched in 2010, successfully used solar radiation pressure for attitude control and demonstrated small but measurable orbital changes from solar sail propulsion. The Planetary Society's LightSail 2 spacecraft, deployed in 2019, successfully demonstrated solar sailing in Earth orbit, raising its orbit measurably by deploying a square sail of mylar and using solar radiation pressure. These demonstrations confirm that the basic physics works and that a spacecraft can be controlled using radiation pressure. The gap between solar sailing in Earth orbit and laser-driven acceleration to interstellar speeds is, however, enormous. For solar sailing in Earth orbit, the relevant quantities are the solar luminosity at Earth's distance, approximately 1,361 watts per square meter, and the spacecraft's sail area to mass ratio. The LightSail 2 spacecraft has a sail area of approximately 32 square meters and a total mass of approximately 5 kilograms, giving an area to mass ratio of about 6.4 square meters per kilogram. The resulting acceleration from solar radiation pressure is approximately 0.00000015 g, leading to measurable but gentle orbital changes over weeks and months. This is useful for orbit maintenance and attitude control in inner solar system applications, but it cannot achieve the velocities needed for interstellar travel. To achieve significant fractions of light speed with a laser sail, the laser intensity must be dramatically higher than sunlight, and the sail's area to mass ratio must be dramatically higher than any currently demonstrated sail structure. The breakthrough Starshot sail would need an area to mass ratio of roughly 1 million square meters per kilogram for the combined sail and payload system, compared to LightSail 2's 6.4. This requires a sail material that is simultaneously highly reflective at the laser wavelength, extremely thin, and structurally capable of maintaining its shape under the enormous laser radiation pressure it would experience during the acceleration phase. The sail must be manufacturable at high quality over the required area with no significant defects, because a local hotspot caused by a reflectivity defect during the acceleration phase would cause local heating that could rupture the sail and end the mission. The deceleration problem is particularly acute for laser sail concepts. Once a breakthrough starshot probe has been accelerated to 20% of light speed and is coasting toward Alpha Centauri, there is no mechanism to decelerate it at the destination. The laser array that provided acceleration is now 4 light-years away and receding. Its beam cannot follow the probe across interstellar space and provide retrograde thrust, both because the beam would need to maintain focus across a growing distance, and because by the time the probe arrives at Alpha Centauri, 8 years will have passed since the acceleration phase, and the laser array would need to have been operating continuously and re-aimed to track the probe's position over that period. Some proposals have suggested using the light from the destination star itself as a brake, reflecting stellar light off the sail to provide deceleration force. The problem is that stellar radiation pressure is very weak compared to what is needed to decelerate a sail from 20% of light speed to orbital speed. And the geometry of using a sail to reflect stellar light for braking while approaching the star at relativistic speeds is complex. The required deceleration distance would be enormous, and the braking force available from reflected starlight is many orders of magnitude less than the braking force needed. For all of these reasons, laser sail concepts, while representing the most near-term credible path toward any interstellar mission capability, are currently limited to flyby missions with gram-scale probes and have no identified path to crewed missions, orbiters, or landers. They represent the first rung of an interstellar capability ladder whose upper rungs remain out of sight. Proxima Centauri as a host star, why the star itself is part of the problem. Any discussion of Proxima b's reachability must grapple with the nature of its host star, because the star determines the planetary environment in ways that are directly relevant to the scientific motivation for the mission. Proxima Centauri is not a star like the Sun. It belongs to an entirely different stellar class, with different physical properties, different activity patterns, and a different relationship to any orbiting planets than the relationship the Sun has with Earth. Understanding what kind of star Proxima Centauri is and what that means for Proxima b is central to assessing whether the destination justifies the journey. Proxima Centauri is an M-type red dwarf star, the most common type of star in the Milky Way galaxy. It has a mass of approximately 0.12 solar masses, roughly 1/8 of the Sun's mass. Its radius is approximately 0.15 solar radii. Its luminosity, the total power output in light, is approximately 0.0017 solar luminosities, meaning it radiates only about 1/600th of the energy that the Sun produces. It is cool enough that its peak emission is in the infrared rather than the visible, giving it its characteristic dim reddish color. At Proxima b's orbital distance of 0.0485 astronomical units, the planet receives a stellar flux approximately 65% that of Earth's solar flux, which is why Proxima b sits within the classical definition of the habitable zone despite orbiting so close to its dim host. What makes Proxima Centauri a hostile host for potentially habitable planets is not its faintness, but its magnetic activity. Red dwarf stars, despite their low luminosity in visible light, are magnetically active, often more so than younger, more massive stars like the Sun. The magnetic activity arises from the fully convective nature of low-mass stars. Unlike the Sun, which has a radiative core surrounded by a convective envelope, red dwarfs are convective throughout their entire volume. This produces vigorous, disorganized magnetic field generation that leads to frequent, powerful stellar flares and coronal mass ejections. Proxima Centauri is one of the more active red dwarfs in the solar neighbourhood. It produces superflares, flares with energies thousands to 10,000s of times greater than the most energetic solar flares observed at Earth, with a frequency of approximately 1 per day. During a superflare, the UV and X-ray emission from the star can increase by a factor of 100 to 1000 above the quiescent baseline for a period of minutes to hours. Proxima b, orbiting at only 0.0485 astronomical units from this active star, receives the full intensity of these flare events with no attenuation from interstellar distance. The UV flux received by Proxima b during a major flare event is estimated to exceed the UV flux that Earth receives from the Sun during quiet conditions by many orders of magnitude. The biological consequences of this radiation environment for any life on Proxima b's surface would be severe. Ultraviolet radiation at the intensities produced by Proxima Centauri's flares would damage or destroy unprotected DNA, disrupt photosynthesis in surface organisms, and ionize the upper atmosphere in ways that could drive atmospheric erosion. Whether life could exist on Proxima b depends on whether the planet has sufficient atmospheric shielding, sufficient magnetic field protection, or sufficient biology adapted to the radiation environment to survive these flare events. All three of these factors are unknown for Proxima b. They cannot be determined from Earth-based observation with current technology. They would be among the primary scientific questions addressed by any mission to the Proxima Centauri system. The stellar wind from Proxima Centauri, the constant flow of charged particles ejected from the stellar corona, is also significantly more intense than the solar wind at Earth's orbit, because Proxima b orbits so close to its star. The ram pressure of the stellar wind on any atmosphere Proxima b possesses would be orders of magnitude higher than the solar wind pressure at Earth. For comparison, Earth's magnetic field provides substantial protection against solar wind erosion of the atmosphere, and even with this protection, the upper atmosphere loses material to space at a measurable rate. A planet with no strong intrinsic magnetic field at Proxima b's orbital distance would potentially lose its atmosphere to stellar wind erosion on geologically short timescales of hundreds of millions of years. Whether Proxima b has a magnetic field of sufficient strength to protect its atmosphere is unknown. The planet's interior structure, and therefore its capacity for generating a dynamo-driven magnetic field, cannot be determined from current observations. What JWST can and cannot tell us about Proxima b. The James Webb Space Telescope represents the state-of-the-art in space-based astronomical observation as of 2025 and is actively being used to characterize the atmospheres of exoplanets through transit spectroscopy. When a transiting planet passes in front of its host star, a fraction of the starlight passes through the planet's atmosphere, and the wavelength-dependent absorption of this light by atmospheric molecules leaves a detectable imprint on the star's spectrum. By measuring this imprint with a sensitive spectrograph, the atmospheric composition of the transiting planet can be determined. JWST's NIR spec and NIRISS instruments have already produced the most detailed exoplanet atmospheric spectra ever obtained, detecting water vapor, carbon dioxide, sulfur dioxide, and methane in the atmospheres of planets orbiting other stars at distances of tens to hundreds of light years. Proxima b, however, does not transit Proxima Centauri as viewed from Earth. Transit spectroscopy requires that the planet's orbital plane be aligned within a small angle of the line of sight from Earth to the star, so that the planet physically crosses the stellar disk during each orbit. For Proxima b, the probability of such an alignment is approximately 1.5% based on the geometry of the orbital system, and observations conducted to detect a transit have not found one. This is consistent with a non-transiting geometry, though not definitive proof, since a transit could occur at a time not covered by observations, or could produce a signal too small to detect with current instruments. The consensus among astronomers is that Proxima b very likely does not transit its star as seen from Earth, which means the primary tool that JWST uses for exoplanet atmospheric characterization cannot be applied to Proxima b. Alternatives to transit spectroscopy for characterizing Proxima b's atmosphere have been proposed and are being investigated. Direct imaging of an exoplanet, in which the planet's own reflected light or thermal emission is separated from the overwhelming glare of the host star, could in principle provide spectroscopic characterization of the planet's atmosphere without requiring a transit geometry. Direct imaging of Earth-scale planets around nearby stars is one of the primary goals of next-generation telescope concepts, including the Habitable Worlds Observatory proposed in the 2020 Astronomy Decadal Survey and the concept mission studied under NASA's Great Observatory Program. For Proxima b specifically, the angular separation between the planet and its host star at maximum orbital elongation is approximately 37 milli-arcseconds, which is within the design parameters of proposed direct imaging missions using coronagraphs or star shades to suppress stellar glare. However, the Habitable Worlds Observatory is not yet funded, designed, or constructed. Its projected launch date is in the late 2030s to early 2040s, and its ability to directly image Proxima b and characterize its atmosphere in detail depends on the contrast ratio achievable between the planet and the star, which for a planet at Proxima b's close orbital distance, receiving only about 65% of Earth's solar flux from a dim red dwarf, is technically challenging. Detailed atmospheric characterization of Proxima b through direct imaging spectroscopy would require significant integration times and favorable observing conditions. The information obtainable would be valuable but limited compared to what an in-situ spacecraft mission to the system could provide. Even if next-generation direct imaging telescopes achieve atmospheric characterization of Proxima b, the information they can extract is constrained by what spectroscopy can detect. An atmospheric spectrum reveals molecular abundances and approximate temperature structure, but not surface pressure, not surface composition, not the presence of liquid water bodies, not geological activity, not any biological indicators below the sensitivity threshold of the technique, and not the detailed three-dimensional structure of the climate system. A remote spectrum is a one-dimensional projection of a three-dimensional atmospheric system. It is immensely useful and would represent a transformative scientific finding. It would not tell us whether Proxima b has oceans, whether it has weather, whether it has a functioning carbon cycle, or whether any of its surface conditions are compatible with life as we understand it. Answering those questions requires proximity that telescopes cannot provide. The minimum technology civilization needed to actually go. Every interstellar propulsion concept that could in principle get a spacecraft to Proxima b within a human lifetime requires technology that does not currently exist, and in many cases requires energy production and industrial capabilities that represent a qualitative rather than incremental advance beyond what human civilization currently possesses. Characterizing specifically what kind of civilization would need to exist to make an actual crewed mission to Proxima b feasible establishes a concrete picture of the gap between where humanity is and where it would need to be. The minimum credible technology base for a crewed mission to Proxima b within a single lifetime begins with a sustained fusion energy economy, in which humanity has solved the engineering challenges of commercial fusion power and is generating a significant fraction of global energy from fusion reactors. This is not merely a matter of having one demonstration reactor. It requires a mature fusion technology that has been deployed at industrial scale across the global energy infrastructure for at minimum decades, with the manufacturing, operational, and maintenance expertise that such deployment implies. The energy required to accelerate a crewed spacecraft to the necessary fraction of light speed is equivalent to multiple years of global energy production at current rates. And providing that energy in a form usable for propulsion requires not just generating the energy, but converting it into thrust with high efficiency. A fusion propulsion system suitable for an interstellar mission would need to generate directed thrust with a specific impulse equivalent to an exhaust velocity of order 10,000 to 100,000 kilometers per second, while maintaining structural integrity and operational reliability over the years to decades of the acceleration phase. No such system has been built, and the engineering challenges involve not just the fusion reactions themselves, but the conversion of fusion energy into directed propulsion, the thermal management of an extremely hot propulsion system, and the structural requirements of a spacecraft that must survive the mechanical stresses of the acceleration phase and then operate in deep space for decades afterward. The development of such a system, starting from the current state of fusion energy research, would likely require multiple decades of focused engineering effort after the basic physics of sustained fusion is demonstrated, and the demonstrations themselves have not yet been achieved. Beyond propulsion, the shielding requirements for a crewed interstellar mission require materials technology and structural engineering that exceeds current capability. The radiation environment of a multi-decade interstellar transit at relativistic speeds demands either very heavy passive shielding of order hundreds of grams per square centimetre of aerial density, which for a spacecraft large enough to house a crew for 40 years would imply a structural mass of tens of thousands of tons just for shielding or active electromagnetic shielding systems that generate and maintain large-scale magnetic fields around the spacecraft to deflect charged particle radiation. Active magnetic shielding at the scale needed for crewed interstellar missions requires superconducting magnets capable of generating field strengths and spatial extents that are far beyond current superconducting technology. The power required to maintain these fields over a multi-decade transit must be provided by the spacecraft's onboard energy source, adding to the propulsion energy requirements. The life support and closed-loop ecology requirements for a crew of any size for a journey of 40 or more years represent an engineering and biological challenge with no current solution. Current space station life support systems are not closed-loop. They depend on regular resupply of consumables from Earth. The longest any human crew has remained in space without resupply is approximately 14 months. Achieved by Russian cosmonauts on Mir and the International Space Station. A 40-year mission requires that every consumable be recycled or regenerated on board with essentially perfect efficiency, that no critical life support system fail beyond the crew's ability to repair it, and that the psychological and social health of the crew be maintained through methods that have never been tested for anything approaching this duration. The artificial intelligence and autonomous systems required to manage a spacecraft of the needed complexity over 40 years without real-time human oversight from Earth represent another area where the needed capability is far beyond what currently exists. A crewed interstellar spacecraft would be the most complex engineered system ever created, combining propulsion, life support, navigation, communication, scientific instrumentation, medical systems, manufacturing capability, and governance structures into a single vehicle that must operate without external support. The artificial intelligence systems needed to manage this complexity, diagnose failures, implement repairs, and adapt to unexpected situations autonomously over decades would need to be genuinely capable of general problem solving at levels that current AI systems do not approach. Taking these requirements together, the minimum technology civilization needed to send humans to Proxima b is one that has achieved sustained fusion energy, developed fusion propulsion systems, tested and operational in the solar system, mastered closed-loop life support ecology for multi-decade space missions, developed active radiation shielding at the needed scale, and created AI systems capable of genuinely autonomous complex spacecraft management. None of these is individually impossible over a sufficiently long development period, but none is imminent, and the combination of all of them being necessary means that the timescale for any crewed mission to Proxima b is measured in centuries at minimum if humanity's current trajectory of technological development continues at roughly its current pace. The self-fulfilling silence of the nearest star. There is a specific irony embedded in the fact that the nearest known potentially rocky exoplanet orbits the nearest star to our own Sun. It is as if the universe arranged things to maximize the temptation while also maximizing the frustration. Close enough to be discovered with a ground-based telescope, close enough that light from Earth reaches it in just over 4 years. Close enough that in a galaxy spanning 100,000 light-years, the distance is essentially zero, and yet far enough that every proposed means of crossing it runs into the same wall of physics and engineering and time. This proximity has shaped the scientific and popular discourse around Proxima b in ways that are worth examining carefully, because the framing of the planet as a neighbour, as next door, as the closest candidate, colours how the difficulty of reaching it is perceived and discussed. When people learn that Proxima b is the nearest potentially rocky exoplanet and that it orbits the nearest star to our Sun, the natural inference is that it is more reachable than other exoplanets. In a literal sense, this is true. The distances to other candidates at 20, 40 or 100 light-years are proportionally greater. But the reachability gap between Proxima b and any other exoplanet in current catalogues is small compared to the gap between Proxima b and anything humanity has ever reached. The nearest exoplanet and the most distant exoplanet are both, from the perspective of current human technology, effectively equally unreachable. Varying the distance by a factor of 10 or even 100 does not change the category of difficulty, because the fundamental problem is not that Proxima b is too far. The fundamental problem is that interstellar space is in a completely different category of distance from anything within the solar system. The self-fulfilling silence of the nearest star is the silence of a destination that can be seen, named, characterized, and dreamed about in extraordinary detail while remaining physically inaccessible. Proxima Centauri appears as a faint reddish point of light in southern hemisphere telescopes. It has been observed thousands of times. Its properties are measured to high precision. Proxima b's orbital parameters are known. Models of its possible climate states have been constructed. Simulations of its atmospheric chemistry have been run. Papers have been published about whether its surface could support liquid water, whether a magnetosphere could protect it from stellar wind erosion, whether its biosphere could survive the flare radiation environment. This body of scientific work is real and valuable. It represents genuine scientific progress toward understanding the nearest planetary system, and none of it has brought humanity any closer to physically crossing the 42 trillion kilometres that separate Earth from that system. The scientific attention devoted to Proxima b is not disproportionate. It is the most plausible nearby exoplanet target, and characterizing it as thoroughly as remote sensing allows is the correct scientific strategy in the absence of the capability for in situ investigation. But the discourse around Proxima b sometimes conflates the scientific importance of the planet with the physical accessibility of the planet in a way that makes the crossing seem more tractable than the physics supports. When scientists describe Proxima b as our nearest neighbour in the search for life, they are making a statement about distance. When science journalists and documentary producers describe it as the nearest world beyond our solar system, they are making a statement about distance. Neither is wrong, but both allow the listener to import the intuition that neighbours are reachable, an intuition that the actual 42 trillion kilometres brutally contradicts. What actually has to change for this to become possible? The question of what specifically would need to change for a mission to Proxima b to become possible is more tractable than the broader question of whether it will ever happen. And it is a more productive framing because it identifies concrete, physical, engineering milestones rather than gesturing vaguely at technological progress. Understanding the specific gaps is the first step toward closing them, and being clear about the gaps also clarifies the timescale on which closing them is realistic. The most fundamental requirement is an energy source capable of providing the required propulsion energy at the needed power levels. The energy needed to accelerate a multi-ton scientific payload to 10% of light speed, including the fuel for deceleration, is equivalent to several decades of current global energy production at 100% efficiency. No existing or near-term energy source can deliver this on the required timescale. Fusion energy, if and when it becomes a mature technology, would provide the energy density needed to make interstellar propulsion energetically conceivable. But fusion energy must first be achieved for terrestrial power generation, then scaled to the capacity needed for industrial-level energy supply, and then adapted for space propulsion applications. The most optimistic timelines for commercial fusion power place the first operational plants in the 2030s to 2040s. Fusion power at the scale needed to provide the energy for an interstellar mission would be decades further out. A propulsion technology capable of applying that energy as directed thrust is a separate requirement from the energy source itself. Fusion energy and fusion propulsion are related but distinct engineering challenges. Using fusion reactions to heat a propellant and expel it as thrust, the nuclear thermal fusion approach requires a compact fusion reactor that can operate at high power density in space. Using fusion reactions to generate electricity that then accelerates ions or drives a laser, indirect approaches, adds conversion efficiency losses. Using the fusion reaction products themselves as thrust, the direct fusion drive approach studied by groups at Princeton and elsewhere requires magnetic confinement geometry that works both as a fusion reactor and as a magnetic nozzle. None of these approaches is ready, but the direct fusion drive approach is the one that could, in principle, achieve the exhaust velocities needed for interstellar relevant speeds. Its development timeline, from the current stage of laboratory-scale experiments to a space-qualified engine, is estimated by researchers working on it at 20 to 40 years from a serious funded program. An aggressive shielding solution must be developed and tested. The most promising near-term approach is active magnetic shielding, in which superconducting coils around the crew compartment generate a magnetic field large enough to deflect incoming charged particles before they reach the crew. Recent studies, including work by the European Space Radiation Superconducting Shield Project, have investigated the feasibility of miniaturized high-temperature superconducting coils for this purpose. The technology is promising but not ready, and the power requirements for maintaining the needed field strength over a multi-decade transit are substantial. Passive shielding using water as a radiation absorber, which has the advantage of doubling as part of the water supply, can supplement active shielding and reduce the field strength needed, but water is heavy, and the mass trade-offs constrain how much can be carried. The biological knowledge needed to design a closed-loop life support system for a multi-decade crewed mission is currently incomplete in specific, identifiable ways. Long-duration closed ecological experiments have been conducted, but none at the scale or duration needed for an interstellar mission. The specific microbial and plant ecology needed to maintain atmospheric composition, recycle water and waste, and produce food in a completely closed system requires empirical study across timescales of years to decades. This is scientific research that can be conducted without waiting for propulsion technology, and that should in principle be proceeding in parallel with propulsion development. The artificial intelligence and autonomous systems capability needed for the spacecraft has the clearest short-term development path of any of the required technologies. because AI development is advancing rapidly across many domains with enormous commercial and scientific motivation. Whether current trajectories of AI development will produce the general problem-solving capability needed for autonomous spacecraft management within the relevant time frame is uncertain. But it is the requirement that seems least likely to be the binding constraint on mission feasibility compared to propulsion and shielding. The planet that defines our civilization's true location in history. There is a sense in which Proxima b is not primarily a scientific problem or an engineering problem, but a civilizational mirror. The question of whether we can reach it reflects something fundamental about where humanity is in its development as a technological species, not just in the specific capabilities related to space travel, but in the broader sense of what kind of civilization we have built and what kind of future we are building toward. We are a civilization that has been spacefaring for about 70 years, if the beginning of the space age is marked by Sputnik in 1957. In those 70 years, we have reached Earth orbit, landed on the Moon, sent robotic emissaries to every planet in the solar system, and pushed one spacecraft beyond the solar system's boundary. These are genuinely remarkable achievements. They represent a compression of exploratory capability that has no parallel in human history. And they leave us still, by every physical measure, at the very beginning of the trajectory that would eventually lead to interstellar capability. The solar system is our neighborhood. We are just beginning to understand our neighborhood. The nearest star is 4 light-years away, and we have barely gone 1/10,000th of that. Civilizations can be characterized by the energy scales they can harness and direct. The physicist Nikolai Kardashev proposed in 1964 a classification of civilizations by their energy use. A Type 1 civilization controls the energy available from its home planet, approximately 10 to the 16th watts. A Type 2 civilization controls the energy of its home star, approximately 4 times 10 to the 26th watts. A Type 3 civilization controls the energy of its home galaxy. Current human civilization uses approximately 2 times 10 to the 13 watts globally, roughly 300 times less than the total energy available from Earth's surface. We are not yet a Type 1 civilization. The energy requirements for interstellar travel begin to approach Type 2 levels. The gap between where we are and where we need to be to cross interstellar space is measured not in engineering progress, but in the entire developmental trajectory of human civilization. Proxima b, in this light, is not a destination that is frustratingly close and technologically just out of reach. It is a destination whose inaccessibility accurately reflects the current state of human development. We are a civilization that has recently, in the last few generations, developed the scientific understanding of physics and the rudimentary engineering capability needed to begin thinking seriously about interstellar travel. We are nowhere near having the energy, the propulsion technology, the materials science, the biological knowledge, or the institutional structures needed to actually accomplish it. The planet 4 light-years away is not mocking us. It is correctly located in the sense that the difficulty of reaching it is appropriate to where we are in our civilizational development. This framing is not pessimistic. It is calibrating. A civilization that currently cannot cross 4 light-years may be a civilization that, in several centuries, has solved fusion energy, developed interstellar propulsion, sustained a multi-generational scientific and exploratory tradition, and begun the first tentative reach beyond the solar system. The trajectory from here to there is not mapped and not guaranteed, but the distance to Proxima b and the specific physical reasons the distance is currently uncrossable define exactly what must be accomplished along that trajectory. Every engineering challenge described in this script is a specific, identifiable problem that points toward a specific, identifiable area of scientific and technological development. The problem is not that Proxima b is impossible to reach in some absolute sense. The problem is that it is impossible to reach with who we currently are. The reality of 4 light years. The actual reason reaching Proxima b has become impossible is not a single reason. It is a cascade. The distance is not merely large, but large enough that no propulsion system derived from current technology can cross it within any human lifetime. The rocket equation ensures that chemical propulsion cannot come close to the needed velocities. The energy requirements at relativistic speeds exceed global energy production by orders of magnitude. The interstellar medium erodes and irradiates any spacecraft at the speeds needed for a practical mission. The deceleration problem doubles the already impossible energy budget. The communication delay makes real-time mission support impossible. The host star bathes any planet it might host in radiation that may have stripped its atmosphere before we even discovered it existed. The planet's basic properties, its radius, its mass, its composition, its atmospheric state, remain unconstrained by any current observation. And the biological, institutional, and AI requirements for a crewed mission exceed current capability so far that no development timeline connects them to the near future. Each of these problems is real. Each of them is grounded in physics that does not bend to engineering ambition. And each of them, viewed honestly, describes not a reason to give up on the dream of Proxima b, but a specific roadmap for what human civilization must accomplish before that dream can be anything other than a dream. The universe has not placed the nearest potentially rocky exoplanet 4 light-years away as a cruelty or an accident. It has placed it at a distance that accurately reflects what it takes to become a civilization capable of crossing interstellar space. And it is waiting with the patience appropriate to something that has been there for billions of years, for us to become that civilization. We are not there yet. The nearest world beyond the solar system is, for the civilization we currently are, unreachable. But unreachable is not the same as unreachable forever. It is a statement about today, not about every tomorrow that follows.